All right, so when you have a fractional power of a complex number, it really means you're looking for the solution of the following. See, this means you're looking for the cube root of negative 1 plus I, right? Because 1/3 power is same as the cube root. And what does it mean by cube root? Cube root means you're looking for the solution, or you're looking for a number whose cube is equal to what's inside. Okay. Now, in the real context, usually you're only looking for the real value as the only answer, right? Cube roots of a real number is a real number, so you always look for the real number. In fact, what happens is there are two other complex numbers which could be cube roots, but we don't take that when you're usually doing cube roots of a real number. But when it comes to a complex number, this has an ambiguity because there are three different possible answers. You know that there are three answers to this, right? Which one you pick? You can't choose. So when it comes to the context of complex numbers, such a question will have three answers, not just one, okay? Because there's no natural one to pick. All right, so let's try that. Now the key is to change both of them into polar form or Euler form. Both are good, but since I've already shown you how to do it using polar form, let me show you how to do it in Euler form. Okay? So let's see, negative 1 plus I. How do you change this into Euler form? So both in polar form or Euler form, you need its modulus and the angle. Okay? So modulus is sometimes also called magnitude of a complex number. How do you calculate it? It's square root of negative 1 squared plus 1 squared. And while you do this, please do not include the I in there. In the formula, there's no I. Okay? Some people make the mistake of putting I squared here and end up subtracting. That's not what this is supposed to be. It's simply the coefficient of I and the real part, square, and you take the square. That's how you do the modulus. And that gives you square root of 2. And then we also have to find the argument of negative 1 plus I, which is just sometimes called the angle. And the formula is what? It's tan inverse of B over A, right? Yeah, B over A. So B is the coefficient of I, so it's 1. And A is negative 1. And then you have to do plus alpha, where alpha is some additional stuff that you add depending on your quadrant. So if you're on the right side, that's in the natural domain of tangent inverse. So there's no problem on the right side. What goes wrong is when your angle actually lies in the second quadrant or the third quadrant. In that case, you have to modify your answer by either pi or negative pi. Okay. You either have to add 180 degrees or subtract 180 degrees. Yes?
You find out what quadrant you're in after you calculate the tan inverse of those?
Yeah. So you need to know what quadrant this is in order to figure out what alpha we should be using. Okay? All right, so what quadrant is this in? It's in the second one, right? Because it's you're going left or going up. Right? So this should be pi. This one should be pi. Because negative 1 means you're going left, and I as positive 1, that means you're going up by 1. Therefore, you're in the second quadrant. Therefore, you have to add pi. Okay, now this 1 divided by negative 1 is simply negative 1. But tangent has this nice property that if you have a minus inside, you can pull it outside. And that's something nice to know. If you have tangent inverse or sine inverse, the minus can come outside. which is not true for cosine inverse. Cosine inverse causes some headache if it has a minus inside, okay? Same is true for tangent function and the sine function. Sine of a negative number, negative comes outside. Tangent of a negative number, negative comes outside. But cosine of a negative number is same as cosine of the one without it. Okay? So cosines don't really care if the thing that you're plugging in is a negative number or a positive number. It gives you the same answer. Okay? All right, so this is what I did. I pulled the minus outside, and 1 over 1 is 1. What's tangent inverse of 1? When does tangent become 1? When does it have the value of 1? 45 degrees, right? Now, oh, I forgot to say, the Euler form is r e to the I theta. This is what you call the Euler form. And r is the modulus, and theta is the argument. One thing that's different from the polar form is when you're writing in Euler form, you have to use, by convention, you have to use radians. Okay, people never use degrees in here, so we should be using pi over 4 instead of 45 degrees, which gives you 3 pi over 4 as the angle. Okay. Now, since I have modulus of square root of 2 and angle of 3 pi over 4, now I can write negative 1 plus I as radical 2 e to the I times 3 pi over 4. So I'm saying that this number is same as this number, although they look very different. They're exactly the same number. Okay. Now let's do the same for z. I can take z as r e to the I theta, because I don't know what r is, I don't know what theta is, so I'm just writing z as some general complex number. In that case, what is z cubed? I have to take the cube of it, which is r cubed e to the I 3 theta. Is that right? Because this exponent distributes to both of them, right? And when you take cube of e to the I theta, this 3 gets multiplied to I theta, so you get I times 3 theta. Yes? Okay. And what we're really doing is we're basically doing the de Moivre's theorem. De Moivre's theorem says that if you take the cubed, the magnitude gets cubed, while the argument gets multiplied by 3. That's de Moivre's form. Okay? And then now we are ready to go back to the original equation and substitute z cubed by this and negative 1 plus I by this. Okay, so let's see what we get. We get r cubed e to the I 3 theta equal to radical 2 e to the I 3 pi over 4. And I'm saying that this equation is now equivalent to this equation. They're the same thing. Now for these two numbers to be the same, their magnitudes, their modulus, the size of the complex number has to be the same. Whereas, for the angles, what do you know? Do they have to be same? They have to be coterminal. It doesn't have to be same. It could be same, or it could be coterminal. That's the key. Okay? And coterminal means you can add 360 degrees over and over again. Right? Any two angles that's 360 or multiple of 360 apart, they're coterminal, right? And in this context, it's 2 pi, so we can add 2 pi. What's 2 pi? 2 pi is 8 pi over 4, right? So when I add 8 pi to this, that's 11 pi over 4. And I can add another 8 pi to this, that's 19 pi over 4. And you can go you can do this forever, but we stop at 3. Why? Because this is cubed. Right? So we stop right here. And then when we solve both of them, we get r equals to cube root or 1/3 power. So let's first rewrite square root of 2 as 2 to the 1/2 power. It's the same thing, right? And taking the cube root is same as taking the 1/3 power. I like this because then I know what to do. I have to multiply these, so it's 2 to the 1/6 power. So you're free to write either in this way, or you can also write it as 6th root of 2. Either one is fine. So that's the value of r. Whereas angle theta is, if you divide 3 pi over 4 by 3, that's pi over 4. Because 3 and 3 cancels. But these two, there's nothing to cancel, so you have to say 11 pi over 12 and 19 pi over 12. So that's what you get if you divide every one of these by 3. So if you divide every one of these by 3, 3 cancels and 3 cancels, but these, when you divide, you end up multiplying by the denominator. Okay? So those are the answers. And now we have almost everything. We just have to write down the answers. How do you write it? In the question it says to write down the answers in polar form, so let's just write them down in polar form. So here, the answer is that it's 6th root of 2 angle pi over 4, if I take this pair it with the first angle. And then 6th root of 2 angle 11 pi over 12. And then 6th root of 2 paired with this, you get 19 pi over 12. Now the question I have in this paper says, in addition, write one of the answer in a rectangular form. Now these I don't know how to write in rectangular form because it's not one of those special angles. See, I only know the sines and cosine of pi over 4 family, pi over 6 family, and pi over 3 family, right? So I know that this is the only one we can write in rectangular form. So let's try that. What's the formula for writing down a polar form into rectangular? If you have r angle theta, that's same as r times cosine theta plus I sine theta. So using this, we have 6th root of 2 angle pi over 4 is equal to 6th root of 2 cosine of 45 degrees plus I sine 45 degrees. And hopefully you know the value of these. Those are radical 2 over 2, radical 2 over 2, and therefore, well, let's see. I guess here it's better to use fractions. This is they all have the base of 2, and when you multiply these two add, when you divide you subtract, so it's, in both cases it's really 1/6 plus 1/2 minus 1. Minus 1, and then, let's see, that's 1/3, no, 2/3 minus 1, so it's 2 to the negative 1/3 plus I times 2 to the negative 1/3. So that's what your answer is. So this is one of the answer in rectangular form. The other two, you can't write down the rectangular form without the aid of a calculator or with some more harder formulas. Yes?
Do we always need to use the Euler form to solve this?
No. I was just trying to show you how to do this in Euler form. If you were to use polar form,
Yeah,
you can do the exact same thing. So up till here it will be the same.
yeah, that's what
But the equation you get won't be this. Rather, it will be if you take z as r angle theta, then De Moivre's formula says z cubed is r cubed 3 theta. Okay, that's equivalent to this result right here.
Yeah.
And then you can say r cubed 3 theta is equal to this one, radical 2 with angle is 3 pi over 4. So using this, you can again get to the same conclusion that the modulus should be same, but the angle should be coterminal.
So we don't have to use Euler formulas.
You don't have to. I just wanted to show you how it can be done.